We will now take up our discussion on generalized Westergaard equations. This is necessary because we have looked at Westergaard stress function, we have also looked at modified Westergaard stress functions. What are the modifications that we have looked at? We have looked at a modification introduced by Irwin. He added minus sigma naught x to the sigma x stress term. So, he added one more term in the series. This was one of the modifications. The other modification was introduced by Tada, Paris and Irwin. What he did was, instead of simply taking only the first term, when you are simplifying z naught is very small compared to a, he had expressed the denominator as a binomial series and allowed as many terms that could be used. But if you really look at, it was not predicting any fringe order along the crack axis. At least the modification by Irwin said that you need to have a constant fringe order along the crack axis. But what you see in reality, in certain situations you see fringe patterns like this. So, what you find here is along the crack axis you have many fringes. You have fringes forward tilted as well as a frontal loop, and this is obtained in an experimental scenario. Unless your basic equations of stress field explains this phenomena, the solution is not complete. See, if people have not looked at photoelastic fringes, they would not have raised a question like this. This shows something has gone wrong in our solution development. So, we have to have a relook at it. And what is the kind of modification that you can think of? Sanford introduced an additional stress function yz to Westergaard stress function capital Zz to explain this behavior. You know, this is very unusual. See, you have taken a stress function. In most of the problems, somebody gives you the stress function, you only ensures whether it satisfies the boundary condition, whether it satisfies the biharmonic equation, and then you proceed with it. You never question whether the stress function is complete or not. In fact, you wanted tau xy to be 0 along the crack axis, that stress function was giving it. But I had emphasized in our earlier discussion, though we wanted tau xy to be 0 along the crack axis, without our emphasis, the solution what we got from Westergaard stress function was the maximum shear stress was also 0 in the case of Westergaard stress function, as well as the modification by Tada, Paris and Irwin. We did not want it, we only specified tau xy to be 0. We did not impose the maximum shear stress also should be 0, but what the solution you got was the maximum shear stress was also 0. So, in the case of actual experimentation, you find there is a variation of maximum shear stress. So, this needs to be explained. So, from this standpoint, Sanford introduced a additional stress function capital Yz. Is it justifiable? This also we have to look at it. And the Airy stress function is modified in this fashion. You had earlier seen phi equal to real part of z double bar plus y imaginary part of z bar. This is what we had seen for the mode 1 problem. Sanford introduced an additional term y imaginary part of y bar, where the stress function y is given as function of two other analytic functions xi and chi. See, the moment you introduce something like this, the proof of our introduction is what? It should explain what is seen in an experiment. So, when I have a very generic solution, particular cases should reduce to what are the simplified cases which we had seen earlier. If it satisfies that, then we can accept, but whatever the solution that we are getting now is the most general form of stress field equations or the most general form of stress functions for the given problem, that kind of a understanding that we could develop. And what Sanford did was, in theory of elasticity, you have a very famous approach known as Kolosov-Mushkelishvili approach for solving problems using complex variables. So, he used this approach to explain the additional term y imaginary part of y bar. In fact, you could see some of this in his publication. This was published in 1979 by Sanford. The paper was a critical re-examination of Westergaard method of solving opening mode crack problems, appeared in Mechanics Research Communication. So, you could go and have a look at that paper, and before we get into this Kolosov-Mushkelishvili approach, we will also look at the relevance of this kind of fringe pattern. Why this fringe pattern was taken as the candidate to verify the inclusion of the stress function y. Let us now look at the typical mode 1 fringe patterns. If you look at here, you see the boundary of the specimen, and I have a crack coming from one of the edges, and this is known as a single edge notched specimen. I have a crack from this edge, I have the other edge shown here, and if you look at crack is somewhere in the middle or slightly less than the middle. So, the A by W ratio would be something around 0.4, it is not 0.5, but A by W is around 0.4. And you could also have a situation where the crack length becomes longer and longer, and the crack becomes closer to the free boundary. So, what people have noted is, when the crack goes very close to the free boundary, you have the frontal loops developed like what we had seen earlier. And if you look at the Irwin's modification, for a crack which is short enough, the fringes are forward tilted, that aspect is captured by Irwin solution, and it showed a constant fringe order along the crack axis. So, this modification will not be applicable when the crack length increases further and comes closer to a free boundary. See, if you recall, we in fact got the frontal loop situation for the case of a crack in a pressurized cylinder. The crack was long enough, it was close to one of the boundaries of it, and I also mentioned it is in a stress concentration field. So, in that case you got a frontal loop. People also have noticed when the crack length is longer in the case of SCN specimens, you have a frontal loop. And we also noticed earlier, by modifying what is sigma naught x, the sign positive or negative, the characteristic fringe patterns you see near the crack tip changes totally. When it is negative, mind you, in my solution I have taken minus sigma naught x. In that minus sigma naught x, when sigma naught x is positive or sigma naught x is negative, is what is given in these interpretations. So, only those type of representation should be looked at, only then this positive and negative has significance. So, here I have cracks tilted backward, and this kind of a situation is seen in the case of a different type of specimen known as rectangular double cantilever beam specimen. We have already looked at double cantilever beam, we had very thin top and bottom portion. Suppose I have that broad enough and I have a specimen long enough like this, in that situation if you have a crack and if you have the loading is applied, you find the fringes are backward tilted. So, people are happy with Irwin's solution that by changing the sigma naught x suitably as positive or negative, they could analyze short cracks in SCN specimens and they could analyze short cracks in the case of RDCB specimens. Suppose in this specimen also if the crack advances and comes closer to the boundary, imagine that this is the boundary of the specimen, then again experimentally it is recorded the fringes have forward tilted loops and a frontal loop. So, people have seen when the crack tip is closer to a boundary and it is long enough, you invariably have frontal loops. That means, maximum shear stress varies along the crack axis. So, this needs to be captured in your representation of the stress field. If it is not captured, then you are not able to satisfy what is observed in experiment. Only here the approach of Kolosov-Mushkilishvili has helped. So, on the axis of symmetry shear stress is 0. By defining y as above, the condition reduces to, because the first term what you have is y times the function comes. So, when y is 0, that term automatically goes to 0. So, shear stress being 0 along the crack axis reduces to imaginary part of y z equal to 0. See, if you really recall the way that we satisfy the boundary conditions when we looked at the mode 1 situation, we looked at what happens for the first set of boundary conditions, what happens at the crack faces, and the second set of boundary conditions what happens at infinity, but the third condition we did not do anything, because we wanted on the crack axis shear stress to be 0, we did not even have any option for us to look at how the boundary condition behaves, it was automatically satisfying, we had no difficulty at all. Apparently we thought we had no difficulty, but when you compare the result with the experiments, it was found that it was lacking in something. So, now what we will see is the condition is modified as imaginary part of y z equal to 0. So, by changing what way we take capital Y, we would have control on how this condition is going to dictate the problem. Suppose I take capital Y equal to 0, which is very similar to what Westergaard did, no function like y exists at all, then I get Westergaard stress functions. The expression of stress field would be same as what you see in the Westergaard solution, and you will also have to set 2 xi prime equal to capital Z, then I get the conventional Westergaard solution. You have sigma x, sigma y, tau x y given, sigma x is nothing but real part of capital Z minus y imaginary part of Z prime, and sigma y equal to real part of capital Z plus y imaginary part of capital Z prime, and your tau x y is nothing but minus y times real part of capital Z prime, and this is straightforward. You are setting y as 0, and how do you get Irwin's modification? We finally want imaginary part of y z equal to 0. One can also set y as a real constant. When you say y as a real constant, its imaginary part is 0. So, what you will have to look at is the condition tau x y equal to 0 is still satisfiable by taking y appropriately. This kind of a luxury we did not have. When you had only one stress function, we were getting the solution, we carried on with it, because Westergaard in his paper he also solved a variety of problems for which on y equal to 0 tau xy was 0. So, people never looked at closely what is the kind of difficulties one would see in the case of a crack problem. When people compared the result with the experiment, they felt something more needs to be done. So, one of the earliest modification was done by Irwin. So, if I have to get the Irwin solution, you take capital Y equal to A and set 2 xi prime equal to capital Z minus A, then one gets sigma x sigma y tau xy in this fashion. So, I get real part of capital Z minus y imaginary part of capital Z prime minus 2A. This will explain for your additional stress term sigma naught x, and sigma y and tau xy, they are very similar to what you had obtained in the conventional Westergaard solution. Now, what I am going to do is I am going to have y present, but we will only ensure that the imaginary part of y z equal to 0. This is what we are going to emphasize. So, if I do this and if I take 2 xi prime equal to capital Z minus y, I get the generalized Westergaard equations. I have sigma x sigma y tau xy, and this is given as sigma x equal to real part of capital Z minus y imaginary part of capital Z prime minus y imaginary part of capital Y prime plus 2 times real part of y, and sigma y is given as real part of Z prime, real part of Z plus y imaginary part of Z prime, y imaginary part of y prime. So, this is an additional term in comparison to Westergaard solution, and finally, you get tau xy equal to minus y real part of Z prime. Then you have 2 additional terms, minus y real part of y prime minus imaginary part of y. Now, we have gone through a circuitous route. We looked at Kolosov-Mushkelishvili formulation. We provided a justification. In a most general case, an Airy stress function is represented in terms of 2 analytic functions. From that argument, the Airy stress function for Westergaard problem also should have 2 stress functions. So, you can have capital Z and capital Y as the candidates. We have still not looked at what is the form of capital Z and capital Y. I could also get this expression directly from differentiating the Airy stress function. Whatever the result that I have got here could also be obtained from this expression of Airy stress function. So, we had looked at what is the stress and displacement field in the case of mode 3. I again emphasized these are valid very close to the crack tip. Then we moved on to raising the fundamental question, the fringe patterns that are seen in a photoelastic experiment show that maximum shear stress varies along the crack axis, whereas the conventional Westergaard and modified Westergaard do not capture this phenomena. To capture this phenomena, Sanford came forward and introduced an additional stress function y, and whatever the stress field you get in terms of capital Z and capital Y, he termed it as generalized Westergaard equations. From the generalized Westergaard equations, by appropriately choosing the function y, you could get Irwin's modification as far as the basic Westergaard solution. I am just going to give you the stress function and the stress field. I will not get into the mathematical details, and the Airy stress function takes this form. imaginary part of y 2 double bar. Since we are discussing mode 2, I have put a subscript 2. When we discussed mode 1 situation, we simply gave capital Z and capital Y. We did not give the subscript 1 there. Since we are discussing specifically the mode 2 situation, we are putting the subscript 2 here. So, I have stress function phi as imaginary part of y 2 double bar minus y real part of y 2 bar plus real part of z 2 bar. If you recall, the singular solution which we obtained had only this minus y real part of z 2 bar. These two terms are additional. Once area stress function is defined, it is possible for you to get the stress field, and I would write the stress field in the form of stress functions only. I have sigma x, sigma y, tau x y, and sigma x is given as imaginary part of y 2 plus y multiplied by real part of y 2 prime plus real part of z 2 prime plus 2 imaginary part of z 2, and you have sigma y is given as imaginary part of y 2 minus y multiplied by real part of y 2 prime plus real part of z 2 prime, and the shear stress tau x y is given as minus y times imaginary part of y 2 prime plus imaginary part of z 2 prime plus real part of z 2. So, now you have the generalized mode 2 Westergaard solution. So, if you look at the form of the stress function z 2 and y 2, you can construct a series solution, and what is mentioned is the stress functions y 2 and z 2 have similar form as their mode 1 counterparts. And what are the mode 1 counterparts? The mode 1 counterparts, you had this function z and y given as a series solution. So, you need to go for a series solution like this, and you have to ensure that z 2 real part of z 2 is 0 on the crack faces to satisfy the boundary condition there. Similar to mode 1 situation, here also imaginary part of y 2 should be 0 on y equal to 0, and we also look at the kind of stress fields that we saw for the mode 1. Something similar to this I would like you to work it out for mode 2, and the expressions are like this. You also wrote down these expressions, and I said they are very clumsy. We have also written down Williams eigen solution results for 6 terms. They were also very difficult to write. Now, we will go and see the solution given by At-Laurie and Kobayashi, and they are the most elegant form of stress field expression, and you have to write this down very carefully. I have sigma x, sigma y, tau x y. So, these expressions give only Cartesian stress components, and this is given as summation of 2 series. The first series involving the coefficient capital A 1 n, the second series involves capital A 2 n. So, the first series is meant for mode 1 loading, whereas the second term in the series is meant for mode 2 loading, and n varies from 1 to infinity. I have n by 2 a 1 n r power n minus 2 divided by 2, and for sigma x I have this as 2 plus minus 1 power n plus n by 2 cos n by 2 minus 1 theta minus n by 2 minus 1 multiplied by cos n by 2 minus 3 theta, and for the sigma y stress term it is 2 minus 1 whole power n minus n by 2 multiplied by cos n by 2 minus 1 theta plus n by 2 minus 1 multiplied by cos n by 2 minus 3 theta, and for shear stress it is minus of minus 1 power n plus n by 2 multiplied by sin n by 2 minus 1 theta plus n by 2 minus 1 sin n by 2 minus 3 theta. See, you will have to notice one thing. I have the mode 1 stress field as well as mode 2 stress field in terms of generic expression. When I change n, I would get the second term, third term, fourth term and so on. I can easily computerize the set of equations. That is advantage number 1. And another aspect is it is easy for computerization. And what you will have to look at is this solution was reported in Handbook of Experimental Mechanics first, and it had 1 or 2 small typographical errors. Even a change in minus or plus sign or a sign to cos can cause havoc. So, these expressions are edited, they are as accurate as possible, and these are used to reconstruct a fringe pattern for complex problem situation, which we would also see in this class. So, take some time in writing these expressions as accurately as possible, because these equations are verified free of any typographical errors. For mode 2, this is minus of summation n equal to 1 to infinity n by 2 a 2 n r power n minus 2 divided by 2, and for sigma x it is 2 minus 1 power n plus n by 2 multiplied by sin n by 2 minus 1 theta minus n by 2 minus 1 sin n by 2 minus 3 theta, and for sigma y it is 2 plus minus 1 power n minus 1 by 2 n by 2 multiplied by sin n by 2 minus 1 theta plus n by 2 minus 1 sin n by 2 minus 3 theta minus of minus 1 power n minus n by 2 cos n by 2 minus 1 theta minus n by 2 minus 1 multiplied by cos n by 2 minus 3 multiplied by theta. And you can again look at the expression, ensure that no sign change or sin or cos change is done in your expression. And how the coefficients are defined? See, we are interested in 1 or 2 coefficients, because we want to find out what is k1 and k2, and the second term in the sigma x stress field for mode 1 situation we label it as sigma naught x. How the coefficients are related to the quantities that we already know. So, that is given here. I have A11 is given as k1 by root of 2 pi, please write this down, and as I mentioned earlier, the terms involving A1 corresponds to mode 1 loading, the terms involving A2 corresponds to mode 2 loading, and A21 is related to minus k2 divided by root of 2 pi. This minus and minus becomes plus, that is how it is written. So, I can find out, if I know the coefficients as part of the solution, I can find out what is k2 and k1, and the second term in the sigma x series is related to sigma naught x in this fashion. 4 A12 equal to minus sigma naught x. And we would see the utility of these expressions. Showing such long expression is not going to enthuse you. You just make an observation of this animation, and what you see on the right side is the experimentally obtained fringe pattern. I have a crack, I have forward tilted loops as well as frontal loops, and on the left side you have the solution obtained from experiments, which is done by a over deterministic least square methodology, and the number of terms in the series solution are incrementally increased. You would notice it is for 4 parameters, 5 parameters, 6 parameters, 7 parameters and 8 parameters, and you can also notice that the values of k1 and sigma naught x change as a function of number of parameters. Now, what I want you to look at is, I will magnify this picture. You see red dots. These red dots are the points selected from the experiment. So, that is an input to your algorithm. If time permits, maybe towards the end of the course we will look at the algorithm, otherwise you can look at the reference and know what the algorithm is. So, the idea is these are all the experimentally obtained points, and from these data you evaluate the series coefficients. Using the series coefficients, replot the fringe pattern, because you know how to calculate the maximum shear stress, and you also know what is the material stress fringe value for the given problem. Using that, it is possible to reconstruct the fringe pattern. The idea is the reconstructed fringe pattern should closely match the experimentally obtained data. So, what I want you to make an observation is, as the number of terms changes, how the geometric features of the fringe change, and as the number of terms are increased, you will find the geometric fringe pattern match with the experimental data. Simultaneously, also notice the variation in the values of k1 and sigma naught x. These are two pertinent parameters in the case of a mode 1 situation. So, I will repeat the animation. So, it is going for 5 parameters. At 6 parameters, the contours match. You find 7 and 8, there is hardly any change. So, beyond 6 parameters, whatever the complicated fringe contours which you observed in an experiment is very nicely captured from your post processed results, and the final value of k1 and sigma naught x are given here. K1 is 0.656 MPa root meter and sigma naught x is 2.919 MPa, and we look at what happens in the case of a 2 parameter solution. We start from a 2 parameter solution. We do not start from Westergaard's singular solution. We said even for short cracks I cannot rely on Westergaard's singular solution. I have to have minimum of 2 parameters. So, when I have minimum of 2 parameters, what do I observe? I only get forward tilted loops, and the fringes are not matching with the experimental data. You see red dots several places. And what is the value of k? K is only 0.445, whereas sigma naught x is quite high. See, if I take a 2 term solution and if my k is same as what I am going to get with a 6 term solution, I do not have to worry. But what you find here is a 6 term solution gives k as 0.656, here it is for 8 term solution, which is higher than the k for 2 term solution. So, which definitely says that you need to go for higher order terms, otherwise k1 evaluation is erroneous. Not only this, we have seen in sufficient discussion that people have looked at the second term in various ways, and we have been saying you should get the second term as part of your solution. Whatever the solution gives, you may have to take it. If I take a 2 term solution, I get sigma naught x is 4.436, but it does not remain constant. 2 term solution is not sufficient to model this situation. So, interpreting sigma naught x equivalent to the far field stress field, that kind of discussions are not completely correct. Let us look at what happens to a 3 term solution. So, for 3 parameter k changes, sigma naught x changes, and you find the frontal loops are not at all matched. You go to 4 terms, there is semblance of formation of frontal loops, and you find k is steadily increasing and sigma naught x is diminishing. 5 terms it is slightly better, and if I have 6 terms, all the fringe features are captured, and beyond 6 terms what you find? The solution stabilizes. I know this is done by a non-linear least squares analysis. The coefficients A11, A12, A13, A14, A15, A16, they were calculated based on the experimental data. It is a very sophisticated algorithm. Based on that you replot and you find for this problem at least 6 parameters are required to model. And when you are having a least squares approach, there is no guarantee that your final solution is correct. Here, in order to ensure that my final solution is matching with the experiment, the fringe patterns are reconstructed and you ensure that we have converged to a proper minimum, so that the solution is indeed representative of the stress field. Now, you find there is quite a variation in the geometric features. We will also have a look at what happens in the case of holography. You look at what way the fringes change for 2 parameters, 3 parameters, 4 parameters, 5 parameters and 6 parameters, and what do you find? You do not find a great change in the geometry. See, we have been discussing for the crack problem, we wanted tau xy to be 0 on the crack axis. Westergaard solution turned out a surprise that tau maximum is also 0, which is incidental, we did not want it, whereas the experiment shows there is a variation of maximum shear stress along the crack axis, which is beautifully captured when you go for a 6 term solution. So, the final understanding is it is desirable that you go for multi-parameter stress field solutions and evaluate the coefficients based on the stress field, and that is how we will have to look at the equations in fracture mechanics. We had looked at multi-parameter stress field equations, and we also saw one example problem where the utility of multi-parameter stress field equations was demonstrated. And what are the equations we saw? We saw the equation by Williams, and you have the 6 term solution in polar coordinates. You get the stress component sigma r, sigma theta and tau r theta, and this corresponds to the mode 1 loading, and you have another set of terms which corresponds to mode 2 loading. This equation is quite clumsy, and we are not in a position to write it in a generic form, and the credit for bringing out multi-parameter stress field equations in an elegant fashion goes to At-Laurie and Kobayashi. And here you have the terms expressed in terms of the variable n varies from 1 to infinity, and you have terms corresponding to mode 1 and terms corresponding to mode 2. The advantage of such an expression is it is easy to write a computer software which would take as many terms as possible for data processing. and in these solutions if you take as many terms as possible, it closely models the stress field. That argument is valid. We had looked at modification of Westergaard equations by Tada, Paris and Irwin. They also got a series solution, but that series solution had only one stress function capital Z, which was inadequate. This was pointed out by Sanford. He added capital Y, then you got the generalized Westergaard equations, and those equations are valid for the given problem on consideration, and you could take as many terms, and the more terms you take, the data processing would be more relevant from experimental analysis point of view. All this show that we are converging into an understanding that multi-parameter stress field equations are a necessity. Though the origin of these approaches are different, they converge to a unique solution. We will also see that. So, what you will have to keep in mind is, from the uniqueness theorem of elasticity, there can be only one solution to every problem. This you have to appreciate, and this is very important. And whatever we have got from Williams solution was in polar coordinates. If those stress components are transformed to Cartesian coordinates and compare it with At-Laurie-Kobayashi, you take the reference as A1i and A2i. A1i is nothing but C1i of Williams solution, and A2i is nothing but minus C2i. So, the solution given by Williams and At-Laurie-Kobayashi are not different, they are one and the same. There is an equivalence, and this was brought about for the first time by my students. This appeared in International Journal of Fracture, and the topic of the paper was equivalence of multi-parameter stress field equations in fracture mechanics. Now, this is a logical step forward, because when you have multiple solution for a same problem, they have to be identical. If they are not identical, then you have to go back and check your mathematics and see whether there have been any mistakes in the development of the solution. And this again gives us a confidence that we are proceeding in the right direction as far as crack problems are concerned. Now, you have seen what is the kind of interrelationship for the At-Laurie-Kobayashi and Williams solution. You can do a similar exercise for Westergaard solution also, and in the class we have developed for the mode 1 situation, and the interrelationship is the coefficient A I of I plus 1 equal to C I divided by I plus 1. For the case of mode 2 loading, I have given you the Airy stress function. I would appreciate that you take that as a home exercise. So, this shows that the multi-parameter stress field equations are not different. One methodology you had complex variable approach, another you had eigen function approach, they converge to similar solutions.